I think it's going to start. Yeah, it started recording. Hi, everyone. I have a great pleasure of hosting here today for the talk Jukka Suomela from Aalto University. And, well, Jukka, up to you.
Yeah, many thanks for inviting me here. So I'll today talk about this paper that we presented at FOCS last year. And we can try to keep this presentation informal. So if you have any questions at any point, please feel free to ask me. So let's get started. As the title of the paper suggests, we are proving lower bounds for maximal matchings and maximal independent sets. And especially we are doing this for distributed algorithms for solving these problems. So we are studying here two classical graph problems, maximal matching and maximal independent set. And a matching is simply a set of pairwise non-adjacent edges, and we say that a matching is maximal if you can't add anything more to it. So it's not a strict subset of another matching. And an independent set is a set of pairwise non-adjacent nodes, and again, an independent set is maximal if it's not a strict subset of another independent set. So you can't add greedily anything more to it. And now it's very important to note that from the perspective of, let's say, classical centralized sequential algorithms, these are completely trivial problems. You could just start adding nodes or edges in an arbitrary order until you get stuck. And that's a feasible solution. But these are very interesting from the perspective of distributed algorithms. So this is our topic today. And by this distributed setting, I mean the following perspective. If you're looking at something like, let's say, maximal independent set in a distributed setting, it's very useful to think about it as follows. You are a node in the middle of a large graph, and you need to pick your own part of the solution. You need to announce whether you are going to be part of this independent set or not. And all other nodes are going to do the same. Every single node in the graph is going to choose whether it's outputting a 0 or 1, indicating whether it's part of the maximal independent set or not. And all of those outputs, they must form a globally consistent solution for this maximal independent set problem. And now, if all nodes see everything about the graph, then we are back to the centralized sequential setting. Then the problem is trivial. But now, what we would really like to understand is how much better we can do. Can we solve these problems so that each node only sees their own local neighborhood? And based on this information in their local neighborhood, they make decisions. And the key question here is, how far do you need to see in the network? Now, just a couple of technicalities. If you start to think about these kinds of questions, for instance, in a setting where the graph structure is very regular, like you have a long path, then it immediately becomes obvious that, okay, in the middle of a long path, all nodes see the same graph structure in their local neighborhoods. So if you apply some kind of a deterministic rule that maps local neighborhoods to local outputs, then in a long path, you can't do anything unless you have a little bit of some extra information that you can use for local symmetry breaking. And we're going to study two different settings. One is deterministic distributed algorithms, which means that we assume that there are some globally unique identifiers that are given to the nodes. So these identifiers come from an adversary. You can't assume that these identifiers are nice, something like, for instance, an increasing sequence of numbers, but there is a promise that these are at least unique. So your identifier is definitely going to be different from the identifiers of your neighbors. And another setting that we're going to study is randomized algorithms, where we assume that nodes are now labeled not with these adversarial unique identifiers, but they are labeled with some random strings of bits. So this is the setting that we are studying. We are looking at maximal matchings and maximal independent sets in these kinds of settings. And a bit more formally, when I say that we care about how far you need to say, this idea is formalized in this model of computing called the local model. And this is a really convenient model because here we can think about algorithms from two complementary perspectives. One perspective is this perspective that I already described. You are a node in the middle of a large graph, and we just ask how far you need to see. And another perspective that at first seems very different is that you think that all nodes are computers, all edges are communication links, these nodes are exchanging messages with each other, and you care about the number of communication rounds that are needed until all nodes can announce their local outputs. But it turns out that these two complexity measures are the same. What you can do based on your radius T neighborhoods is exactly the same as what you can do in T communication rounds in this kind of a message passing model. Because after all, if you think about it, in each communication round, you can propagate information for exactly one hop in the graph. So this is the setting. And I'd like to emphasize that we're doing computer science in this traditional thesis sense. So we are interested in the worst case complexity. So we have a worst case setting with the worst case input graph. And for instance, if we have something like unique identifiers, we also are interested in the worst case assignment of unique identifiers. So this is the setting where we are studying maximal matchings and maximal independent sets and also some other graph problems. Is the setting clear? Any questions about this at this point?
If I may ask, are these two equivalent up to like exactly or up to some constants?
It's like up to plus minus half a round or something like this. There's just a minor technicality that you will need to define what is radius T neighborhood in a very specific manner. So there's just a tiny technicality which is related to this thing that in T rounds, you can see nodes, all nodes that are within T hops from you, but you can't be aware of edges that are connecting nodes that are both at distance T from you. Okay. So if you think that like the midpoint of an edge is at distance T and a half from you, then this is precisely equivalent. So there is no multiplicative constant. It's more like plus minus one, and everything is the same.
Okay.
Good. Any other questions about this setting? Okay. So this is the setting where we are studying maximal matchings, maximal independent sets. And when we study distributed complexity of these graph problems, we are usually interested in complexity as a function of these two parameters, n, which is the number of nodes, and delta, which is the maximum degree of the graph. And basically, the old news regarding these problems was that you can find maximal matchings and maximal independent sets in this setting, both with deterministic and with randomized algorithms, in order of delta plus log star of n rounds. Or put otherwise, if all nodes in the middle of a large graph see their delta plus log star of n radius neighborhoods, then it's enough information to produce a globally feasible maximal matching or maximal independent set. So this was the old news. This was already known before our work. And what we basically proved is that this upper bound is tight. You can't do better than this. At least you can't do better than this if your delta is very small in comparison with n. So this is the result that we proved. And they have, I think some of you have already probably seen some presentations about this work where the focus has been more on, let's say, technical details of this proof. But I thought this time I would talk a bit more about the history of this project. Not so much about, let's say, difficult proof techniques, but more about how we actually came up with this proof and what were the key steps that led to this discovery. And this is actually a very old project. For me, this project actually started already something like 9 years ago. And to understand this starting point, we will need to look at the state of the art in theory of distributed computing something like 10 years ago. So what was known in, let's say, year 2010? People in this field, they were very actively studying 4 key problems. 2 of these problems are maximal independent set and maximal matching that we already introduced. And 2 other problems are vertex coloring with delta +1 colors and edge coloring with 2 delta -1 colors. And if you're wondering, like, why exactly this many colors? Well, you can easily say that if you have a color palette of this size, then there is again a trivial centralized algorithm where you can just process nodes in an arbitrary order, and for each node that is uncolored, there's always one free color available, and the same about edge colorings. So this is again the threshold that is trivial for centralized algorithms. So there are 4 key problems that people had studied a lot, and all of these problems are symmetry breaking problems in the following sense. If you are looking at graphs that are very regular, so that your local neighborhoods are isomorphic. Nevertheless, in all of these problems, nodes will need to do something else. They can't just all nodes produce the same constant output. For instance, in all of these problems, you can say that if one node is producing output X, all of its neighbors can't produce the same output X. So some local symmetry breaking is necessary. And there was already a very long line of work dating back to the 1980s where people had proved both upper bounds and lower bounds for all of these problems. But nevertheless, in spite of all of these results, all of these 4 problems were very poorly understood back in, let's say, 2010. What was known was, I mean, a lot of things were known about these problems, but one specific thing that is important for us was that 10 years ago, it was known that all of these problems can be solved in time that is order of delta plus log star of n. And for none of these problems, people had any idea if you can improve on this linear in delta part. This plus log star of n was well understood. People knew that, okay, you can't go below log star of n. But if you're happy with this plus log star of n, then do you really need linear in delta on top of that? Or could you get whatever, square root of delta plus log star of n, or even constant plus log star of n? This was completely unknown. And if you start to think about these kinds of questions, it's actually highly inconvenient to try to reason simultaneously about this dependence on delta and dependence on n, which seem to have very different kind of roles in these algorithms. It seemed to be clear that this plus log star of n is kind of related to symmetry breaking. Any problem that is of this kind of symmetry breaking flavor, you need to have this plus log star of n there. That was known. But what about this linear in delta? What is it doing on top of this symmetry breaking? Why do we need anything like this? And what we started to ask is, can you somehow decompose this problem in this log star of n component and linear in delta component? So the first question is, how do we study dependence on n in isolation without worrying about this linear in delta part? Well, this is actually trivial. You can just set that your delta is constant. Actually, you can even set things like delta is 2, and you just look at paths and cycles, and you already can extract this tight complexity that is order of log star of n. Problem solved. That's easy. But now, what can you do to study dependency on delta? Of course, you can't set n to be constant and expect something meaningful to happen, because if you set n to constant, then your delta is a constant as well, and there is nothing to be done. But we thought that maybe you could somehow try to modify the problem so that you eliminate this symmetry breaking concern from the picture. So we started to ask the following question. Could we find simple special cases or restricted versions of these problems being, for instance, maximal matching, where we would have upper bounds that are not delta plus log star of n, but they would be just linear in delta? And here the answer is yes, there are actually plenty of such special cases. You can either look at fractional relaxations of these problems. Maximal fractional matching has an upper bound that is just linear in delta. Or you can already provide some symmetry breaking information. You can look at bipartite two-colored graphs where this two-coloring is already breaking symmetry. And again, there's a simple upper bound that we will see very soon that is linear in delta. Or you can look at edge-colored graphs where edge coloring is breaking symmetry. Again, an upper bound of linear in delta. You just proceed by color classes. So our idea was...
So it essentially means that you are given some kind of a promise.
Yes.
Like two coloring of vertices or edge coloring of a graph.
Yes, exactly. That's not the whole truth, but we'll come to a concrete example regarding this two coloring of vertices very soon. But somehow
Excuse me, what is fractional matching?
Fractional matching is basically you first write matching as an integer program and then look at LP relaxations. So we are looking at a very specific LP relaxation of matchings. And then maximal fractional matching is basically kind of a maximal solution to this LP, so that you assign values to edges so that you can't increase these fractional values of any edge. So it is, again, kind of a greedy solution that you could find trivially with the centralized algorithms, but again, it's not obvious how to do it in a distributed setting.
Okay.
So now our plan was that there are now all of these problems that have upper bounds that are linear in delta. So could we first try to prove a matching up lower bound for one of these? And if we can do that, could it help us to also prove tight lower bounds of the form delta plus log star of n for the general case? That was the plan. And today, I'll especially focus on this problem of maximal matchings in bipartite graphs, because that's going to be very important for us today. So let's look at this problem in more detail. What I'm going to do is I'll introduce basically a toy problem. This is a simplified version of this question of how fast you can find maximal matchings in bipartite graphs in a distributed setting. I'll try to simplify this as much as possible so that there are as few moving parts as possible. So We're going to look at bipartite regular graphs. So now delta is no longer the maximum degree. Delta is the degree of all nodes. So all nodes have degree delta. And we have a bipartite graph where this bipartition is already given. We have black nodes, we have white nodes. And in this distributed setting, each node knows its own color. And finally, we will simplify the model of computing so that we are not looking at settings where we have randomness or unique identifiers or anything like this. We will just assume that there is a port numbering. So a node, for each node, there is just some arbitrary adversarial numbering of its incident edges. So a node can refer to its neighbor number 1, neighbor number 2, neighbor number 3. That's it. And this port numbering is adversarial. Of course, if you had a friendly port numbering, then you could even encode a solution in this port numbering. But this port numbering is basically now the only adversarial component here. And again, we'd like to find a maximal matching in this bipartite regular graph. Something very simple. So we would like to now figure out how fast you can do this. How many communication rounds are needed, or put otherwise, how far does a node need to see in order to pick its own part of the solution, where its own part of the solution is simply whether I'm matched or not, and what is the port to which I'm matched. And if you start to think about this setting, there is a very simple algorithm that solves this in time that is linear in delta. And the algorithm is simply the following. You start by considering all white nodes. All of them are initially unmatched. All of these white nodes send a proposal to port number 1. Then all black nodes that get any proposals, they will simply accept the first proposal that they get and reject all other proposals. And all of these edges along which we had proposal acceptance pair, they are added to our matching. It's easy to say that what you're getting this way is a matching. And then we continue. Next, all white nodes that are still unmatched, they will send proposals to their port number 2. And then all black nodes that got any proposals will accept the first proposal that they got, if they hadn't accepted anything previously. And again, all of these proposal acceptance pairs are added to our matching. And we continue. Now, if there's still unmatched white nodes, they send proposals to their port number 3, and then again, black nodes that get proposals accept the first that they get, if they are not yet matched. And if you continue this way, after delta steps, each white node has already been either matched or it has been rejected by all of its black neighbors. And if it has been rejected by all of its black neighbors, it knows that all of the black neighbors are already matched. So we have a maximal matching. And you only need here order of delta rounds, because each of these proposal acceptance steps takes exactly 2 rounds. So the complexity of this algorithm is something like 2 times delta rounds. And the key thing here is that there is no dependence on n. The running time is just linear in delta independently of n. You can even run this in infinitely large graphs and it will still stop in finite time.
I have a small question here. Yeah. So do we even need like this port numbers on the right-hand side?
Okay. On the right-hand side, I think the key use for these port numbers is to break ties. If you are a black node, you get multiple proposals in the same round. You will need to somehow pick between those.
Yeah, because it's not sequential, right? It's
yeah. And another a bit more technical reason why we need these port numbers is that we need to somehow define what is our precise model of communication here. So the idea is that the model of communication is such that you get this vector of messages, one from each port, and you can send a vector of messages. And then you need to somehow be able to kind of basically answer to the same node that sent you a message. So we are using these port numbers also for that. And also for the representation of the result, because all of these black nodes have to also tell that, okay, if I'm matched, with whom I'm matched. And they basically output the port number of this edge in the matching. But you're right. In some sense, if you had suitable tie-breaking rules available, then you wouldn't actually need this to kind of run this algorithm.
Okay, thank you.
Good. Any other questions about this? So we have a very simple algorithm that runs, that works in delta regular two-colored graphs. You only need a port numbering. You don't need unique identifiers. You don't need randomness. And it works in linear delta many rounds. Or, as I'd like to emphasize, another perspective is that each node only needs to see up to the distance 2 times delta to figure out whether I'm going to be matched and with whom. Now comes the question, is this optimal? Can you design in this exactly the same setting, in the same model of computing, a faster algorithm? Sublinear in delta, maybe some kind of divide and conquer scheme, like let's split our graph in 2 smaller parts and recursively compute maximal matchings there, combined solutions. Maybe log of delta would be the right answer instead of linear in delta. Or maybe there is some strange graph theoretic reason why actually you can solve this problem in 4 rounds, independently of delta. Because just these port numbers necessarily provide some information that you can use as soon as you see your radius for neighborhood. We had no idea about this. We had no lower bounds. We check with computers that, okay, with large enough delta, you can't solve this in 2 rounds or something like this. But that was basically all that we knew back then.
Are you saying about randomized algorithms as well, or only deterministic?
Actually, here, if you're looking at these kinds of complexities that are independent of n, randomness cannot help because you can basically boost your probability. But our final end result that we will get eventually is actually something that also holds for randomized algorithms. But right now, I'm only considering this toy problem, where we have this seemingly simple toy problem in a toy model of computing, where you have just port numbering, everything is deterministic, no unique identifiers, you know your color, everything is nice and easy. This feels like a problem that we should immediately be able to understand. And this would be like a first small step towards understanding more general problems. So somehow our hypothesis, like back then, like whatever, 8-9 years ago, was that the feeling was that this linear in delta in this very simple algorithm that is just sending proposals and getting acceptance or rejection, it felt that this linear in delta is there for the same reason as why we see this linear in delta in all of these more complicated algorithms that find, for instance, maximal matching in general graphs in delta plus log star of n rounds. So maybe we could analyze this problem, understand it properly, prove that this linear in delta is necessary, and this way get some understanding of this more general problem as well. So that was the plan. And there was some progress since the starting point of this project in around, let's say, 2011. In 2012, we were able to prove that in this edge coloring setting, where we are not given a 2 coloring of nodes, but we are given something like, let's say, linear in delta coloring of edges. In that setting, we were able to prove that you can't solve maximal matching in time that is little of delta independent of n. And we also studied fractional matchings, and we again proved that, okay, little of delta independent of n is not possible in the usual local model. But even though these results gave us some confidence that maybe this linear in delta has to be the right answer, because for these related problems in related settings, we seem to be getting linear in delta lower bounds. Neither of these results told us anything about this toy problem of bipartite maximal matchings. And because they didn't tell anything about this toy problem, they definitely didn't tell anything about the general case. So it seemed like back then we had a lower bound technique that was able to give linear in delta lower bounds. But this lower bound technique was completely unable to handle input graphs that are two-colored. And if you can't even tolerate that, then there is fairly little hope in being able to understand the general case. So there was some progress that was kind of promising in the sense that it gave the indication that linear in delta is the right thing, but we had no idea how to prove it. And there was also progress that was kind of pointing in the other direction. In 2015, Barenboim proved that actually for these coloring problems, you can go below linear in delta plus log star of n. Now things got interesting. So coloring is actually solvable in time that is less than delta plus log star of n. So maybe the same technique could be applied to maximal matching, maximal independence. So what is actually going on here? We kept thinking about this bipartite maximal matching problem. At some point, this was already kind of a running joke in our group, because every time we had any visitors coming to see us, we immediately started to talk about this bipartite maximal matching problem. We asked everybody's opinion on this problem. We tried to convince everyone that this is the right problem to study. Whenever I visited anywhere, I was always talking about this bipartite maximal matching. And so this was definitely not a secret 9-year project for us. This was something that everybody knew that we were really obsessed about. For instance, in 2014, I gave a workshop presentation where I was basically outlining this whole research program with this punchline that, okay, next we will just need to figure out what is the complexity of bipartite maximal matching. And once we do that, we can hopefully understand interesting things. And if you can't do that, then there is no hope of making progress. But in spite of all of these efforts, we seem to be making really zero progress until, let's say, a couple of years ago. Or actually, we thought that there was zero progress. But the truth is that actually progress, very significant progress on this problem already started in the 1980s. Nobody just knew it back then. In the late 1980s, Lineal proved a lower bound that showed that tree-coloring of cycles is not possible in less than log star of n rounds. And this is this key result that tells us also that, for instance, maximal matching, maximal independence set, thanks to all kinds of reductions, you know that those also need this log star of n time. So this was this result that explained this log star of n time. But back then, we had no idea that this is also connected to explaining this linear in delta part. So let's see what Lineal did. The starting point was, let's assume that there is an algorithm that solves tree coloring of cycles in t rounds, where t is something very small, like less than log star of n. And he showed that you can then construct another algorithm that finds in t-1 rounds coloring with a larger number of colors. And then you can repeat this. In t-2 rounds, you can again solve another coloring problem with a larger number of colors. And if you repeat this for these steps eventually you have an algorithm that is solving a non-trivial coloring problem in 0 rounds. And this is, of course, impossible. So this starting point A0 can't exist. So this was what Lineal proved. And of course, everybody knew this result. But I think everybody also thought that this whole proof technique is like something completely ad hoc that only makes sense specifically for graph coloring. And I think everybody thought that way until something like 2016, where when we studied something completely different. This has nothing to do with maximal matchings. We were studying a problem called synchronous orientation because it was related to algorithmic Lobos local lemma. So we wanted to prove a lower bound for that. It turned out that the proof structure that we had was on high level very similar to the proof structure that Lineal was using. We start with this assumption that there is an algorithm that works in T rounds, and we speed it up 1 round at a time. Then we have an algorithm that solves something else in T-1 rounds. And then we repeat and repeat. And eventually we have an algorithm that solves something non-trivial in 0 rounds, which is the contradiction. So what is going on here? There are 2 proofs that seem to have a similar high-level structure. We always kind of do this round elimination, 1 round at a time. And Sebastian Brandt was able to figure out what is really going on here. So this is something that was published last year, but this result was discovered, I think, in 2018. And Sebastian proved that you can take any locally verifiable problem in certain technical sense. No worries about the definition. All of the problems that we have discussed here today are locally verifiable in this sense. And if you start with a problem that has some unknown complexity T, in a completely mechanical manner, you can construct another problem from the same problem family that has complexity T-1. And now you can repeat this and repeat this. And if you can repeat this for k steps and you don't encounter trivial problems, then you know that your origin problem has to have a complexity of at least k. And this is a technique that is nowadays known as round elimination. And the key thing is that this is mechanical and applicable to any problem. Okay. So in 2018, Sebastian had applied this technique to prove a new lower bound for a problem called weak 2 coloring. And we got interested in this, and we invited Sebastian for a research visit just for 4 days so that he could present his proof, so that we could learn about this new lower bound technique. And well, things didn't go as planned. Sebastian started by presenting this general round elimination technique. And then the plan was that he would use then this weak 2 coloring as a running example to demonstrate how this proof technique can be used for something good. But because we are obsessed about this bipartite maximal matching problem, I immediately wanted to say, what would happen if we just blindly tried to use this round elimination in the context of bipartite maximal matchings? Could we use that technique to prove a lower bound? Now, as I said, round elimination is something mechanical, but bad news is that if you just try to apply round elimination in a mechanical manner, you tend to get exponential blow up in the complexity of the description of your problem. So even if you start with something like, okay, let's try to get a feeling of what is happening. Let's look at bipartite maximal matching for, let's say, delta is something small, delta is 10. Let's try to see if we can prove, let's say, a 10-round lower bound by just starting with this concrete case and somehow try to generalize this. Well, you start with problem P0, that is bipartite maximal matching. We understand that. and let's say that maximum degree now is 10 or something small. And you start doing round elimination on whiteboard for a couple of steps. You get problem P1, where we now know that this has complexity exactly 1 round less than the starting point. And this problem still makes sense. But then you do a couple of steps more, and all of a sudden you say that after something like 2 or 3 steps, you already have filled 2 whiteboards with some unreadable description of some complicated, ununderstandable graph problem. And we have no idea how to continue from here. And we have no idea what is this kind of big picture that we could generalize to any given delta here. Now, it was kind of clear that what we needed was to somehow simplify these problems. So instead of strictly following round elimination, looking at those complicated problems that we get out of that, we could at each step simplify, kind of round down or estimate downwards these problems, so that we would have a simpler family of parameterized problems, so that we could understand these problems, we could generalize what is going on here. These problems would be some kind of relaxations of those problems that we get from round elimination. But the key challenge is that we can't relax it too much, because if we accidentally relax these problems too much, maybe these problems become trivial and we won't get any lower bound. So now there is a mechanical technique, and then there is this intuitive idea that we would like to somehow relax these problems that we get out of this mechanical technique. But how do we do this actually? Now, if you have some kind of a very complicated graph problem that is dealing with some kind of labels on nodes and some kind of constraints related to these labels, there are many systematic ways in which you can try to simplify these problems. Maybe let's say if you have labels that are numbers between 1 and 10, maybe you can just merge labels 1 and 2 so that these 2 labels are interchangeable. And you can try to merge all kinds of labels in all possible ways, and then see what happens. Maybe we first fix one simplification scheme, try to do round elimination simplification, see if we seem to be making progress or if we seem to have a dead end because we accidentally simplified too much, and then try another scheme. But if you try to do this with pen and paper or with whiteboard, it's painful. Round elimination is mechanical, but this exponential blow up at every step is not really helping you. So, and after all, we had this challenge that Sebastian was visiting us only for 4 days, so we had to work quick. So a key idea was that Dennis Olivetti actually at one evening implemented this whole round elimination procedure as a computer program that we could use to automatically see what actually happens if we start with this problem, do round elimination, do these simplifications, do round elimination again, and see what happens. And by basically having this automatic tool for doing these experimentations was what actually led to this breakthrough that enabled us to discover just the right simplifications. And once you have just the right simplifications, you will get what we were really looking for. And actually you can get a lot more. We didn't get just a lower bound that showed that this delta plus log star of n is the best that you can do. But we also got lower bounds that show that even if you have a somewhat worse dependence on n, like something like plus whatever, square root of log n for randomized algorithms, you still need to have this linear in delta there. So these were the final results that we got for this original problem of maximal matchings in general in the usual local model, no cheating with the model of computing, nothing like this. And The latest news is, if you checked what happened in stock this year, there is actually a new upper bound for maximal independent set that basically shows that our lower bound up to questions like whether it's log n or polylog n or something like this, up to these kinds of details, these lower bounds are now tied for pretty much all combinations of delta and n. So now, after all of this work, maximal matching and maximal independent set are very well understood. And I'm happy to tell that this Rockeliminator tool, this is this computer program implementation of this Rockeliminator procedure, is actually freely available online. You can even run it in your mobile phone, just open it in a web browser and see what happens when you enter some graph problems and ask, what is a problem that is exactly one round faster? So a lot is known, but there is also a lot that is still unknown. We now know that graph coloring is strictly easier than maximal independent set and maximal matching, but we don't know how much easier. This was everything that I wanted to say today. So many thanks to everybody for listening, and I'll be very happy to take questions.
So I have a question. I was always trying to understand this relation between delta and n, and it's not clear to me. I mean, as I understand, you can get polylog in delta and n by the network decomposition, but on the other hand, you cannot go by your lower bound into sublinear in delta and strongly sublogarithmic. And
yeah,
how does it paint a bigger picture?
I can try to show the picture. So basically, this is the picture. So if you try to see this whole landscape for maximal matching as a function of delta, which is here the horizontal axis, and as a function of n, which is the vertical axis. These blue dots here are randomized algorithms. Like, for instance, this Fisher dot here is something like you can get randomized maximal matching in time that is order of log delta plus polylog log n. So this is something that is possible with randomness. And these open circles, blue circles, are deterministic algorithms. You can, for instance, find this Panconesi and Ricci, which is linear in delta plus log star of n, as I was already mentioning. And all of these orange boxes are randomized lower bounds, and this orange, or this kind of white box with orange boundary is our new deterministic lower bound. So you can see that this landscape has this kind of a funny shape, like you can improve complexity as a function of delta all the way to linear in delta and keep complexity as a function of n very small. But then if you want to get even slightly below linear in delta, you will need to significantly increase complexity as a function of n. So there is no smooth interpolation between these delta and n parameters. There is kind of gap in some sense. You can't get all combinations that you would expect to get. So this seems to be related to this kind of gaps in the landscape of complexity of LCL problems.
A follow-up question is, so if you move a little bit into sublinear in delta and then increase the dependency on n, is there then a similar interpretation of those two terms, like an intuitive understanding? Because for delta plus log star, we have this understanding now.
Yeah.
So no.
This is a very good question. I mean, if the complexity is just a function of n, then it's kind of understandable. Like understanding something like log and randomized, it's kind of easy. But understanding what is like log delta plus poly log n, what is the role of these two components here? I don't have good understanding of that. So I think this is a good open question. I mean, one part of the answer is just something like in some of these regions, you just happen to have strange complexities because there are things like at some point you will run out of nodes in your graph. And your worst case is some specific combination of delta and n where everything is balanced just right so that like this, both this kind of linear in delta part and something that is related to seeing beyond the boundaries of the graph. These are just right balanced. So I think there is no, it might be the case that there is no good understanding beyond this fact that, okay, at some point you just run out of nodes and then things become trivial.
Okay, thank you. Are there any questions from the audience?
So do I understand correctly that you can't get lower than log star n, even though even if you don't care about dependency on delta?
Yes, this is correct. So basically, the lower bound basically already shows that even if your input graph is just a cycle,
okay,
then you can't go below log star of n. So this means that even if you have like anything like f of delta times log star of n, even that won't help you anything. So it's really like log star of n is a lower bound even for delta being a constant.
Okay.
I have a question. So you spent a lot of the talk talking about this bipartite version, and then
Yes.
at the end, this person created this program for round elimination, and it ended up solving the general problem. So my question is, did the bipartite version end up helping you get the result in the end?
So absolutely. So this whole story is so that what we proved was that this toy problem that I introduced, we proved that this requires linear in delta rounds. And then the next step was that we proved that even if you add randomness, and even if you add some dependence on n, you can't do better with this toy problem. And now, basically, this is already enough to get this general result because randomness is already strong enough to construct unique identifiers with high probability. So now we basically had this result that even if you have randomness, even if you have unique identifiers, and even if you had this friendly promise that your input graph happens to be bipartite and bipartition is given and everything is regular, even in that case, you get these lower bounds. And then this lower bound for general maximal matching was just this simple observation that, of course, if you can't solve this special case in this bipartite setting any faster, then certainly you can't solve the general case any faster. But this bipartite setting was really crucial because we were doing this round elimination for this bipartite regular setting. And all of this kind of family of problems that we constructed, these relaxations, everything was about bipartite and regular. So that was critical, really.
There's a question on a chat. Do results on network decomposition have implications on results with complexity expressed as a function of delta?
The short answer is yes. So now, if I remember right, we can also get for maximal independent set these kinds of complexities that are roughly like log of delta plus poly log n. So this was previously known for maximal matching, But now these new network decomposition results basically show that you can do the same thing for maximal independent set. So basically this picture that you are now seeing, this was the state of the art for maximal matching before this new network decomposition results. And now, thanks to these new network decomposition results, we know that the high-level landscape for maximal independent set looks very similar to this. Of course, the precise dots are slightly different, but the high-level landscape is very similar. The structure is very similar, both lower bounds and upper bounds. And this was a surprise. I was not expecting that they are so similar.
Thanks. Another question from the chat. What is your guess on how the complexity landscape of delta+1 coloring looks like?
This is a very good question, because if you go back to this, let me show. I think I had a concrete question here. So this last row, we have a question. Can you find delta+1 vertex coloring in order of log delta plus log star of n? And this seems to be a kind of innocent question, but current upper bounds are exponentially far from this as a function of delta. And current lower bounds are more than exponentially far away from this as a function of delta. So our upper bounds are like square root of delta. Our lower bounds are log star of delta. So we really have no understanding at all about delta+1 coloring. So I would guess that maybe going below log delta is going to be at least very difficult, if not impossible. But I wouldn't be completely surprised if, let's say, log delta plus log star of n turned out to be the right answer. But I really don't know. This is...
We will see in 10 years from now.
Hopefully.
So if I may follow up the last question, so how is it related to like edge colorings? What do we know about edge colorings?
So it seems that edge colorings are known to be easier than vertex colorings. And in the very recent years, we have seen plenty of progress on edge colorings with various numbers of colors, even like even pushing below 2 delta minus 1 edge colors and so on. So it seems that edge colorings might be genuinely easier than vertex coloring. But so it also seemed with matchings and independent sets. At some point, it seemed like matchings are easier maybe than independent sets, but that was just kind of our lack of nice upper bounds. We know that matchings are probably easier in the sense that if you let a student design a fast algorithm for matchings and compare it with designing an equally fast algorithm for maximal independent sets, definitely the student is going to be struggling more with independent sets. But we don't really know if something similar holds for colorings, whether it's just feeling more difficult to handle vertex colorings than edge colorings, or if there is a genuine separation between these two.
Okay, thanks.
Okay, I think we had an extensive session of questions. Thanks, Jukka. Thanks. Really amazing talk. A pleasure to have you here.
Many thanks for inviting me here.